work, important information, part 3. This is our 5th lecture here. This is going to be so important, knowing how to calculate what we call a molar mass. You need to know how to calculate the molar mass of elements and compounds. It is this is like one of our major, you need to know how to do this as soon as we start the school year. So make sure you know how to do this. Before I even talk about all of this, I'm going to just quickly jump over to our periodic table here. This is what your periodic table looks like for AP Chemistry. Yep, as you can see there, it's an AP Chemistry periodic table. They only give you the element symbol, the atomic number, and at the very bottom, we have this thing called the molar mass of the elements. You might recall this from the part 2 summer work important information. So now, every time you look at a periodic table, if you're looking for each element, if you want the mass of a mole of that element, you look at the mass underneath its symbol. So the mass of 1 mole of hydrogen is 1.008 grams per mole. For oxygen is 16 grams per mole. Nitrogen, 14.01. Carbon, 12.01. And I will be referencing these numbers in this lecture. So I'm probably not going to jump back and forth into the periodic table. So you are going to need to make sure that you are able to recognize and have a periodic table in front of you. So let's get into calculating molar masses. So now we define the average mass of a molecule of a compound as its formula mass. The common term we use is molar mass, which is the mass of 1 mole. The way that we calculate this formula mass, or molar mass, is I take the number of atoms of the first element, and I multiply it by the mass from the periodic table of that first element. And then I add that to the number of atoms of the second element and multiply that by its molar mass on the periodic table, and so on and so forth for however many elements there are in the compound. I have an example here. I did it for CO2. I know I wrote a little bit here, but I'll just talk through it and you can copy it. In CO2, there is 1 C and 2 O's. 1 mole of CO2 has 1 mole of C and 2 moles of O. Keep that in mind. And so, if I want to calculate the molar mass of CO2, I need 1 times the molar mass of C and 2 times the molar mass of O, and I add those together, and I get 44.02 grams per mole. Let's do another one. And if you didn't catch that, now I'm going to start from scratch. Let's do the molar mass of C6H12O6, which is glucose. This has 6 carbons plus 12 hydrogens plus 6 oxygens. And on the side here, I don't know if you could see here from the periodic table, I kind of already wrote for us here. Here are the molar masses of the elements of carbon, hydrogen, and oxygen from the periodic table. So there are 6 carbons. So if I want the molar mass of C6H12O6, and then by the way, I always refer to as my little shorthand notation for molar mass. So you'll see written all over the place. So my molar mass of C6H12O6 would be 6 times the molar mass of carbon, which is 12.01 grams per mole. This is for carbon. And then I add that to 12 times the molar mass of hydrogen, which is 1.008. That's hydrogen. And I add that and I'm just going to erase this over here. Sorry, this is in the way. I add that to 6 times 16.00 grams per mole. This would be the molar mass of oxygen. And I had to multiply by 6 because there are 6 of them. If I add and do all that math together, I should get about 180.16 grams per mole. Grams per mole is the units for molar mass. So if I ever see G over M, these are the units for molar mass. Molar mass of an element, molar mass of a compound, molar mass of whatever I'm talking about. Okay? All right. So now let's talk about, after calculating a molar mass, I could use this molar mass as a conversion factor, right? For 1 mole of C6H12O6, that has 180.16 grams. This can be used now as a conversion factor. In the Part one lectures, important information, I taught you about dimensional analysis. That's where we take our given quantity and we multiply by the wanted known conversion factor over the given known conversion factor, and that helps us get our want. And I'm going to show you here right now. So here's a quick example. It says how many grams are found in 2.3 moles of C6H12O6. I'm going to start by writing 2.3 moles of C6H12O6 to remind you of the part one, some important information. If I start with moles, I put moles on the bottom. Whatever I start with, I put on the bottom. That's my given. Whatever I want, which is grams, I put on top. And now look, before my eyes, I know what numbers to put where. The 1 is associated with the mole. The 180.16 is associated with the grams. Boom. Now I could do my math. 2.3 times 180.16, I get 414.37 grams of C6H12O6. Notice how I didn't put per mole, because this is not per mole. This is 2.3 moles. Okay? There's also a trick. If you are not a fan of the dimensional analysis, as I've shown here, this is an equation that you could rearrange and could be given to you on the AP exam. If I take my moles and I multiply it by my molar mass, I'll get grams. Literally right here, look, 2.3 times 180.16, that's moles, times molar mass, I get my grams. I can also do the opposite. How many moles are found in 133 grams of C6H12O6? I'm going to start with my 133 grams of C6H12O6. Whatever I start with or I'm given, I put in the bottom. Whatever I want, I put on top. And before my eyes, I have the units from my conversion factor here, and I know what number goes where. The 1 is associated with moles. The 180.16 is associated with grams. So I'm going to do 133 times 1, and then divided by 180.16, whatever's in the bottom you divide, and you will get 0.7382 moles of C6H12O6. And I want to also make sure that you know that this number makes sense. If 1 mole is 180.16 grams, if I have 133 grams, 133 is less than 180. So I should have a number that's less than 1. I should have less than 1 mole, and I do. I have 0.7382. Okay? So that is calculating a molar mass and then converting between grams and moles. On the bottom here, I'm going to put the not so popular, and we did this in the part 2 important information. If I want to go from moles to molecules or atoms, don't forget something called Avogadro's number. And look, this is not that popular in AP chemistry. I've only seen maybe one question on the AP exam in maybe the last 3 years that may ask you to use Avogadro's number. And it's just like doing dimensional analysis. If I have my moles, I'm going to multiply by 6.022 times 10 to the 23rd over 1 mole. If I have atoms or molecules, I'm going to have 1 mole and divide by 6.022 times 10 to the 23rd. But I'm going to look at important information part 2. Okay? All right. Now, to check your understanding, do exercises 13, 14, and 15. I actually already did the setup for 15 here. I'm actually going to talk about that, and then I'll double back and try and walk you through some answers here. Right? So if you want, you could stop the video here and do the exercises, and then check back on some understanding. Otherwise, I'm just going to make sure that you know that you only have to turn in exercises 13, 14, and 15 for this lecture. So for 15 here, it says how many bromine atoms. The moment it asks for atoms, I have to think about Avogadro's number. Avogadro's number is 1 mole is 6.022 times 10 to the 23rd. Well, before I could get atoms, I need moles. And I gave you grams. That means I'm going to have to go from grams to moles to moles of bromine to then atoms of bromine. Because be careful. I give you 35.2 grams of CH2Br2. That's not of bromine. That's of a compound that contains bromine. So look at my work here. This is why dimensional analysis and this conversion factor method is super helpful. I started with 35.2 grams of CH2Br2. Whatever I start with goes on the bottom. Grams of CH2Br2, and I put mole on top. That's a conversion factor I have. 1 mole of CH2Br2 is 173.83 grams. And so, boom, there you go. Oops, that was erasing. This first step here helps me get moles of CH2Br2. And then we have to be careful about this next one. Think about what I wrote here. 2 moles of bromine atoms for every 1 mole of CH2Br2. I mentioned this earlier on the previous page. 1 mole of CO2 has 1 mole of C and 2 moles of O. Well, same idea here. If I look at my compound here, I'm going to try and do this with a small highlighting. If I look at my compound here, there are 2 bromines in this formula. If I have 1 CH2Br2, I'll have 2 Brs, because this question's asking about bromine atoms. So I have to multiply that by 2 to get the total number of atoms, or moles of atoms. And then once I have my moles of bromine, if I multiply by Avogadro's number, 6.022 times 10 to the 23rd, I will get my total number of atoms. And I'll leave the calculation up to you. Make a star here because this is on your basics quiz when you come back into the school year. I am going to ask you to use Avogadro's number because I want you comfortable with big and small numbers and using scientific notation. All right, I am going to do 2 of your questions here to kind of help you out. So it says calculate the mass of each sample. It says 15.7 moles of HNO3. And I already give you the molar mass is 63. Now, you could do moles times molar mass gives you mass or grams. Or you could do my dimensional analysis setup. I like doing that. 15.7 moles of HNO3 times, well, this conversion factor says 1 mole of HNO3 is 63 grams of HNO3. This is basically a conversion factor. It's a set of numbers that equal each other that I could use to convert between moles of HNO3 and grams of HNO3. So if I have moles of HNO3 for dimensional analysis, that goes on the bottom. If I want the mass, grams of HNO3 goes on top. And so before my eyes, I see that 63.0 is attached to the grams and the 1 is attached to the moles. And I can end up doing my math here. Now I actually have to have a calculator. So I will do 15.7 times 63, and I get 989.1 grams of HNO3. Now be careful for B and C. Ignore this Milla. I don't know what that is. I'm so sorry. That was a typo. For B and C, you are going to have to calculate the molar mass first. So don't forget that I gave you the molar mass in A just so I could show you here. But for B and C, you have to be able to calculate the molar mass and then do the math that I showed you. Okay, and then let's do 1 of 14. I'm going to do B for fun. All right, so B, I'm going to actually calculate a molar mass. So for 14B, it says I have 23.6 kilograms of FeNO3. Don't forget how to name that. This is iron. It looks like each nitrate, don't forget that nitrate is -1. There are 2 of them. That means that iron must be Roman numeral 2. This is iron 2 nitrate. So this is back in the notes. This is how I would name that. And I have 23.6 kilograms. And then I made a note here. 1,000 grams is a kilogram. Well, 23.6 kilograms times 1,000 grams over 1 kilograms, multiplying by 1,000, and I get, very simply, 23,600 grams of FeNO3 2. Why am I using grams instead of kilograms? Well, these molar masses, right? Look at all my notes up here. I'm going to go back for a second. Grams, grams, grams. Everything is in grams. So if I want to do any type of conversions, I got to be consistent with my units. I need grams. So I have 23,600 grams of FeNO3 Well, I want to determine the number of moles. Well, I start with grams, so grams has got to go on the bottom, and moles has got to go on top. Now, a problem here is I need to calculate the molar mass. So if you're still watching here, because you don't have to watch this part, the molar mass of Fe is 55.85. So I'm going to do this over here, FeNO3 Fe, there's only one of them, so 1 times 55.85 grams per mole, plus, be careful here, there's a 2 on the outside of this parentheses here. And I don't know if it was explicitly shown in previous notes here, but that 2 distributes onto the inside. That means I have 2 N's and 6 O's. So I'm going to have 2 times the this is for Fe, 2 times the molar mass of nitrogen, which is 14.01 grams per mole. So there's my nitrogen. And I'm going to add that to 6 times the molar mass of oxygen, which is 16. And so I'm going to do this math on the side here. So I'll do 55.85. Oops, nope, I'm going to use a different calculator. So I'm going to have 55.85. I'm going to add that to 2 times 14.01. And then I'm going to add that to 6 times 16. And I get a molar mass of 179.87 grams per mole for FeNO3 So it's nice to know, and I'll probably bring this up later when we do other notes, make sure that you know that the parentheses multiplies on the inside. So now I know that 1 mole of FeNO3 is 179.87 grams. And I could use this now back in our exercise 15. So I'll jump back there. So I have the molar mass over here is 179.87 grams per mole. So 1 mole will go on top, 179.87 grams goes on the bottom, and now I could do my simple math here. I'll do 23,600 times 1 divided by 179.87, so 23,600 divided by 179.87. We know this number is going to be larger than 1. Whew, that's a lot of moles. 131.21, I'm just rounding, moles of FeNO3 Woo, that's a lot. Rare, but we're working in kilograms, so we got thousands of grams, so I probably have hundreds of moles. Alrighty, that ends me working on some of your exercise problems. And like I said, again, you didn't have to watch this part of the lecture, but I did help you answer some of our tougher problems in the exercises. Now it's all up to you to just do B, C, A, and C for 13 and 14, and then maybe do that calculation of 15, and just submit these questions as your work for this lecture.